The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to the Women in Technology webinar today. Our chapter is all about empowering each other, helping each other out, and personally, forgot to introduce myself. I'm Kathy Kellenberger, co-leader of the chapter, and I'm really excited about helping women become presenters, helping them become technical writers, because that's one way to really take your career to the next level. So be sure to reach out to us if you are interested in becoming a speaker or blogging, that sort of thing, because we would love to help you out. I'd like to thank Century One today. They are one of the sponsors of our chapter, and they've been sponsoring us for several years and have also been the sponsor at our Women in Technology lunch at past summits. So we really are thankful to them. And today we'll be giving away a $100 gift certificate from Century One to one of our lucky viewers. You can find us on YouTube. We have recordings of most, if not all, of our webinars. Take a look at our homepage. We list women who are speaking for the other virtual chapters, as well as women who are speaking at SQL Saturdays and other events. Make sure you join our virtual group to receive our monthly newsletter with news about what's going on and usually an editorial about a topic that's important to women in tech. And be sure to follow us on Twitter as well. On Friday of this week, we are going to have another presentation from Heather Ritchie. She is the speaker who was at past summit. She was our Women in Tech lunch keynote speaker. And we're very excited to have her speaking. Now, if you had signed up before, we had to move the date. It was going to be next week. Heather's going to be traveling, so we just ended up moving it to this Friday. So be sure to watch that. In April, we're going to be having a session on DevOps in the database. And then we also like to promote some of the webinars from other groups. So Steph Locke and Kendra Little will be presenting in the next couple of months as well. So be sure to check those out if those are things that are interesting to you. There are quite a few SQL Saturdays coming up. And here's Rochester, Richmond. Several women will be presenting at each of these SQL Saturdays. We've got Colorado Springs, Madison, Raleigh, Orange County, and also Costa Rica. So go out to our webpage and you can get a list of all of these SQL Saturdays and the women who are speaking at them. So today's session is called, Are You Optimistic About Concurrency? So in this session, Kalen Delaney is going to talk to us about the different optimistic and non-optimistic concurrency options. And it looks like she's also going to talk to us about the in-memory OLTP feature as well. Kalen has been working with SQL Server for over 30 years, and she provides SQL Server training to clients around the world. She's been a SQL Server MVP since 1993, and I think she's been like one of the very first, if not the first, SQL Server MVP. And she speaks at lots of conferences, especially Past Summit, TechEd, and writes lots of books. And I've learned a lot from Kalen over the years. You can find her new website with her training schedule at SQLServerInternals.com, and you can find her on Twitter as SQL Queen. If you have any questions throughout the webinar, please type them in the question box, and I will let Kalen know when we have a question, maybe, during a slide transition. And at this point, I'm going to turn it over to Kalen. And there you go.
And now I'm here. Thank you.
Thanks. So go ahead and I'll let you know if you have any questions.
All right. Well, let me get my screen up. All right. Hello, everybody. I almost said good morning, and then I have to remember not everybody's in the morning. In fact, on the east coast of the U.S., you just crossed over into afternoon, but it's still morning for me. I'm on the west coast of the U.S., and then I'm sure there are many of you in between the coasts and maybe even other places in the world. I can't see the question box. Kathy has to tell me, otherwise I would have said, tell me where you're from, because I'm always excited to find out that there's people listening to me from all kinds of interesting places in the world. So welcome. I'm going to be talking about one of my favorite topics today. Concurrency used to just have to do with locking and blocking, which is still one of my favorite things to talk about. But as of the more recent versions, concurrency can mean other things besides locking and blocking, and I'm going to tell you a little bit about what those other things are. So we're going to look at the two concurrency models and several different isolation levels and see how they're the same and how they're different, both with your regular disk-based tables, which are the tables we've had since the very first version, and there's some slight differences in behavior with the memory optimized tables with the different concurrency models and isolation levels. So, so there'll be just a really quick 30,000 foot overview, or 10,000 meter overview of what the in-memory technology is all about, because I want to focus just on how the concurrency is managed. Let's see if I can do a slide transition here. All right, so Kathy already pointed out most of the key features here. I've been working with SQL Server for a very long time. When I'm working, it is SQL Server. I actually have a life beyond SQL Server. I have 4 kids. I have a grandson. I have a dog. I've got lots of friends. I really like my life. But I really like SQL Server too, and I like working with it and writing about it. My most recent book is the update to the SQL Server in-memory OLTP internals book, which just was released last fall from Redgate. But they make their books freely available for download, so you can check out the Redgate site and just look either for in-memory OLTP or for my name. You should be able to find it. Kathy mentioned my website. I've just had it revamped, and it will be becoming more enhanced, but there will be details about upcoming classes, upcoming presentations. If you want to know if I'm going to be at a SQL Saturday, I'll have it on my website. Actually, I'm going to have to update that slide because I'm going to start blogging through my own website too. But all my past posts you can still see at sqlblog.com, so it's not wrong to have that up there at the bottom of the screen there. So I'm going to talk about what concurrency has to do with and what exactly optimistic concurrency means. The alternative, the non-optimistic concurrency, is the opposite of optimistic, or pessimistic. And these names are not just arbitrary words. Optimistic, pessimistic actually have meaning related to what those words mean in English. But to really understand everything that's going on with concurrency models, we also have to look at the concept of isolation levels and what guarantees they provide for you. The concurrency models actually just tell you or tell the system how the isolation levels will be guaranteed using what underlying mechanisms. And I know that's a little heavy for just getting started, but hopefully by the end of the presentation, it will all be a little bit clearer. So We'll start with just looking at isolation levels and concurrency models and what these terms actually mean and what the different choices are. And as I just alluded to, there are two different concurrency models which actually dictate how the isolation levels are enforced. One of them is called pessimistic, one of them is called optimistic. So after looking at the overview of isolation levels and concurrency models, I'll talk about exactly how pessimistic concurrency does what it does, how it guarantees the isolation levels, and how optimistic concurrency guarantees the isolation levels. And we'll look at that in conjunction with in-memory OLTP or memory optimized tables. Now, as I mentioned also, looking at concurrency is one of my favorite topics. And one of the reasons for that is because it is a crucial performance tuning area that many people overlook. A lot of people, when they think about performance tuning, think about either the system level things, getting the right number of files, the right amount of memory, tweaking your network and I/O systems, or they think about the queries themselves and getting the right indexes and writing the queries in the right way. Is this query structure better performing than this query structure? And what about joins versus subqueries? And we're not going to go there. That is definitely a crucial area in tuning, but you can have the best queries in the world. You can have the most expensive, latest and greatest hardware in the world. You can have the best indexes anybody ever thought of. But if you can't get to the data you need because somebody else has it locked, it doesn't matter how good your indexes and your queries and your hardware are. It's going to seem like the performance is abysmal. If you can't get your data because someone else is doing something with it, performance is going to be horrible. So this is what concurrency is all about. Multiple users working with the same data at the same time, and we want to make sure they can do it without interfering with each other. So we'll start by looking at the isolation levels and the concurrency models just as terms to talk about what they mean and what they do for you. So every connection to a SQL server, every time you open up Management Studio and say, show me or run this query, you are running in a particular isolation level. We're going to have a chart in just a couple of minutes that shows the 5 different isolation levels SQL Server supports, but I will also be listing them or talking about them individually. And each isolation level has certain guarantees that it provides for you. So first I'm going to give you a couple of potential guarantees, and then I'm going to talk about the other side of the coin, the bad things that can happen if you don't have an appropriate isolation level. Then once we talk about what can be guaranteed and the bad things that can happen, then we'll see the chart for the different isolation levels and what each one guarantees, and then I'll explain the 2 concurrency models. So when you're thinking about what interaction you want your session to have with other sessions, what do you want the system to be able to guarantee? What do you want to be able to trust? There are 2 consistency guarantees that we usually think about, and you may not think about it in these words, but the ideas behind them are definitely something that you should consider. First of all, there's something called read stability. Read stability means that if you are in a transaction and you start reading data, select from my table, select from that other table, as long as your transaction is open, you will continue to see the same values. Read stability means not only will you continue to see the same values, but the values you read will not change. And I know it sounds like those are the same things, but I'm going to show you at the end that those aren't the same thing. So You want the data that you've read to stay stable, or you might want the data you've read to stay stable. That's a guarantee you can ask for. You read it, nobody else can change it. The other guarantee you might choose to ask for is something called phantom avoidance. And to understand that, of course, you have to know what a phantom is. A phantom is a mysteriously appearing row that just like shows up in the middle of your transaction. So let's say you ran a query that says, show me all the customers who live in Mazatlan. How many customers do you have in Mazatlan, Mexico? Well, maybe you've got 44 customers, and then you're in a transaction looking at these 44 customers, and then you look at the query again, how many customers are in Mazatlan, and now there's 45. An extra row appeared because of something that somebody else did. That row that's appeared is a phantom row. Read stability is talking about the actual data values changing. Phantoms are talking about a whole new row appearing. So if you don't like that idea, if you don't like a whole new row that meets your conditions appearing, you want to make sure you avoid phantoms. How you do that, we're going to get to that. But I just want you to understand these concepts because I'll be talking about them going forward. Is it important that you have read stability? Yes or no? You answer that for your applications, for your workloads. Is it important that you have phantom avoidance? Yes or no? You need to answer that for your workloads. I can't answer those for you. But another way to look at these behaviors is from the opposite perspective. We can look at them from the behaviors that we want to not happen instead of the behaviors we want to guarantee. So the ANSI SQL Committee, that's the American National Standards Institute, when it discusses transaction interaction, has defined 4 what they call bad dependencies. And I know that's so judgmental to call them bad. They may just be things you might wish to avoid. And you can see at the bottom of the list, we've got phantoms again, but there's actually 4 on this list. The things that most people think about wanting to avoid, first of all, lost updates. Now, I know I've told you these are just decisions you make, but it turns out that almost everybody wants to avoid lost updates. A lost update happens when 2 users are updating the same data at the same time. So let's imagine a ticket selling application and 2 different users are at 2 different workstations looking at the available tickets for Saturday night's concert, and they both see that in the 3rd row, seats A and B are available. A and B in the 3rd row are vacant, and I want to buy them, but they're pretty expensive, so I have to go talk with my significant other. And while I'm doing this, another user is also seeing that 3rd row seats A and B are available. Both users are looking at these 2 seats available, and what if they both decide to purchase them at the same time? One of them will do the update and think they've got the seats, and then the second one will come in and do the update, and it will think it has the seats. Only one of them is the winner. Which one? Well, that has to do with the actual technical implementation that there's no way to look at here, but one of the updates will be lost. The seat can only be assigned to one user. So, depending on how the system handles this, one of the users could have their updates lost. And this is usually something most people want to avoid. It's not a good thing when it happens. I will give you a little heads up here. SQL Server pretty much avoids lost updates no matter what you try to do. If you want lost updates, you have to try really hard. We're just talking generically for now. The second bad dependency is something called dirty reads. Dirty reads happens when one user, one transaction is in the middle of updating data and they have not yet committed it. Another user can read the uncommitted data. Is this a good thing or a bad thing? And I know some of you might say, oh, I do that and nothing bad happens. Well, I'm going to add another word to that. Nothing bad has happened yet. There's no way to guarantee the data. If you ask for dirty reads, you're basically saying, I don't care anything about my data quality. I strongly recommend not using this, but it is your choice to ask for dirty reads. Dirty reads mean reading uncommitted or invalid information. The third behavior that we may want to avoid is something called non-repeatable reads, which is very closely tied to read stability. But a non-repeatable read is reading some data within a transaction and then reading different data, different values for the same rows in a subsequent read. Is that a good thing or a bad thing? Again, you get to decide. And phantoms happening, obviously, is the opposite of phantom avoidance. So this slide is the bad things that we may want to avoid. The previous slide was whoops, I'll get back to the chart in a minute. The previous slide, this is looking at it from what we want to guarantee. This is looking at it from what we want to avoid. We can approach it from either direction.
Kalen, I have a couple of questions for you. One of them is just a housekeeping question. Will the slide deck be available for download at some time? So you can send it to us and we can put it on our website, or what would your plans be for
Well, my plan is to figure out how to post it to my new website, and that hopefully will be happening by the end of the week.
Okay, cool. The other question is really interesting. It is.
Now, is it an interesting question or an interesting answer?
It might be both. I don't know.
Okay.
Something I hadn't thought of before. Would deadlocks be lost updates?
No, because a deadlock prevents one of the changes from happening. I mean, and you get an error message when the deadlock occurs. So a lost update is when you actually overwrite one of the updates. And that doesn't happen in a deadlock. I update and say, okay, this is my seat, and someone else comes along and overwrites my update. That doesn't happen in deadlock. Deadlock, two processes are trying to update the same value, and one of them is kicked out. So only one of them gets to do the update, and the person who was kicked out knows they got an error. So they know they didn't get what they want. The problem with lost updates is you may not realize, like, what if it wasn't a ticket selling application? What if it was an airline application and you got to the flight and someone else had your seat? Now, does this ever really happen? Yeah, this can happen, and you don't know it until you get to your flight. That's the lost update. Okay. Deadlock is not the same thing, but yes, that is a very interesting question.
All right, that is it for now. Thanks.
Okay, so along the top here, and sometimes in these presentations I can actually do screen writing, and other times I can't. Let's see here. Nope, it's not letting me write, but I think there is a pen from the system, but we didn't check that out before. Oh, there we go. Look, drawing tools menu. Hold, please. Drawing tools. Let's see if I can do this. Look at that. All right. Remember, those bad behaviors. We're not listing lost updates because that's nothing anybody ever requests. But sometimes you might request dirty reads. You might say that non-repeatable reads are okay. You might say that phantoms are okay. So the isolation levels, and I'm going to change this color here. Let's see if it lets me change the color to purple. Okay, down the left-hand side, we have the isolation levels that SQL Server allows you to specify. Whoops, no, I didn't change that correctly. Hold on, a pen. I want a pen with a color. Okay, there we go. Read uncommitted is isolation level 1. Read committed, which happens to be SQL Server's default, so I'll put a star by it, is number 2. Repeatable read is 3, and serializable is 4. Now, I'm not just putting these numbers down to make sure that I can use this pen here. These numbers are important. Those of you that are familiar with looking at SQL Server's metadata, you know a lot of times when there's a numerical value, there's also another column in the metadata that translates the value, but that does not happen for isolation levels. I'm going to show you when we get to the first demo that there is a way to look at what anybody's isolation level is, and it just gives you the number. So these 4 numbers are the ANSI specified isolation level. The ANSI SQL committee specifies these 4 levels. There's a 5th one that Microsoft added to SQL Server in 2005. Other products might have added it at some point, but it is not part of the ANSI specification. So each of these isolation levels tells us which of these behaviors is allowed or not allowed. Read uncommitted, for example, does allow dirty reads. How you get into that, that's not part of this talk, although I'm sure some of you are aware of that. But read uncommitted allows all these behaviors. It allows non-repeatable reads. It allows phantoms. We're going to see this in just a minute in the first demo. Read committed is SQL Server's default. Read committed does not allow dirty reads. No, but it does allow the other 2. Repeatable read only allows phantoms, and serializable doesn't allow any of these behaviors. Now, this update conflict at the end, I'm not going to talk about yet. We're going to see the same chart again a little bit later after we talk about optimistic concurrency. And I'll also explain what the words in green mean, no, but, and yes, but. Why are these special cases here? Just look at the 1, 2, 3, 4 for now. This is what SQL Server had all the way through 2012. Version 2012 gave us the 4 isolation levels with these behaviors. We did have snapshot isolation, but there were some differences with snapshot until memory optimized tables came about. I'm going to show you some demos of the main isolation levels in just a minute, and hopefully that will make it a little bit clearer. And I'm realizing this chart still has an old past banner from when I gave this at the Los Angeles SQL Saturday last year. Oops, sorry about that. I meant to clean this up a little more. All right, so then, is this, no, oh, there we go. No, now I can't go to the next slide with the pen on. All right, come on. Okay, do we have a GoToMeeting expert out here? It's not, I'm not seeing how.
I wonder if I make me a presenter and then
normal, wait, normal draw. No, I don't know yet. I turned off drawing mode and there we go. Whoa, okay. I need to erase all my drawings, don't I? To erase, there we go. All right, so we've talked about the isolation levels now. The next thing I want to mention is the concurrency models. Basically, what the concurrency models tell us is how to enforce the isolation levels. Isolation levels are universal in multi-user systems, but how they get enforced is up to the implementation. So one choice is pessimistic, which uses locking and blocking. How do you prevent somebody from reading dirty data? You lock it. How do you prevent the data from changing after you've read it? You lock it. Locks are used to guarantee the behaviors that you want. As you change your isolation level, you change how many conflicts or blocking situations there are. As you change your isolation level, you can actually change the duration of your locks. And in some cases, you can actually change the type of your locks where you don't have time to go into all the details of locking. I just want to point this out that this is what pessimistic concurrency is all about, locking. And through version 2012, well, not completely. There's some fuzzy stuff there, which is part of what I want to talk about. Through 2005, pessimistic concurrency was all that we had. The only way that your behaviors were guaranteed was by locking data and then have other users blocking. The alternative is optimistic concurrency. But we'll get to that in a minute. So let's look at the pessimistic concurrency in action. I have a demo here, and I'm using an old sample database, but you could do basically the same thing on any tables that you had. I'm going to be using a very old sample database just because I know the data so well. This is an old database called Pubs with very small tables with just a few rows, but I know them very well. So, and there will be a script. I will make not only the slides, but the demos available. And you will also have a script for creating this database. So I am using internal version number 14, which is SQL Server 2017. But what I'm going to show you now can be run in any version back through 2014. And I'm running the RTM version of SQL 2017. I mentioned the metadata just a minute ago, that you can look at your transaction isolation level. You can actually look at it for any connection. It's actually kept track of in the metadata or in the dynamic management view called DM exec sessions. DM exec sessions has the column called transaction isolation level, and I want to look at it just for my session. And I can see that by looking at the session ID equal to at SPID is my session. So transaction isolation level 2 is the default, is read committed, which means no dirty data, but I might have non-repeatable reads and I might have phantoms. So let's look at that. In the Pubs database, I'm going to make sure I'm in read committed, even though I just saw that I was. If I got out of it, I could get back to it with this set command here. I'm going to look at the data in one of the tables. There's a table called titles, which is a bunch of books. We have the title ID, a title, a type, a publisher ID, a price, and a bunch of other information. There are 18 rows in this table. So this is the default behavior. I start a transaction and I do an update. I update one of the prices, one row affected. Now, in another connection, while this transaction is still open, somebody else tries to look at the average price from all the titles, and they can't do it. They are blocked. This is SQL Server's default behavior. No dirty reads. If I looked at the average price here, it would be giving me uncommitted data because this session has done an update, but it has not committed it yet. So this session over here is blocked and is waiting until this one either does a commit or a rollback. Once it's commit or rolled back, then we can see the average price here, $14.22. That's the default behavior. But how is the next isolation level different? Well, I'm going to stay in read committed for the next example, but show you a different operation where my transaction is first going to just do a read, just do a select. Select the average price, $14.22, we just saw that, but I'm inside a transaction. Now another transaction is going to try to do an update, and it will succeed. Even though we're in a transaction, it didn't stop the other process from doing the update, because remember from the chart, in the default read committed, non-repeatable reads are not guaranteed. I had a price of $14.22. When I go look at it again, it is now $14.77. The data changed out from under me. It is not guaranteed. Now that my transaction's over, actually nothing much changes here. But if I change my isolation level to repeatable read, change to repeatable read, I'm going to jump back to the top. And it says I'm now in, oh, I got out of grid mode. I'm in level 3, repeatable read. Now I'm going to do the same thing again. Look at the average price, $14.77. Now when this guy tries to do an update, it will block. Now nobody can change the data that I've read because of my isolation level. How is SQL Server preventing this update from happening? It's happening because of the locks in repeatable read isolation. This first session locked the data as it read it, and it's holding on to those locks until the commit happens. So when it goes back and looks at the value again and again and again, it never changes. The reads are repeatable. The data is locked, and this process can't change it until the first one comes along and says, oh, I guess I'm done. Let's commit that. Now this one could finish. One row affected. And now if we look at the average, only after the transaction is committed can that average change, can the values change. So I'm going to close these windows. I don't want a lot of clutter. And we'll look at the final example here. The difference between repeatable read and serializable has to do with phantoms, new rows appearing. So I am still in repeatable read, but we'll just guarantee that. Now I'm going to look at rows which meet a certain condition. Look at rows where the title ID starts with these two letters, and there are 4 such books. BU is actually all my business books, and we can see there are 4 of them. Now another session is going to try to do an insert. It's going to insert or try to insert my SQL Server 2012 internals book, and it actually will be successful because this is a whole new row coming in, and repeatable read isolation does not prevent phantoms. So when I go back and look at the same query, I get a whole new row. I have 5 rows here now. 1 more in addition to the 4. This is my phantom row, allowed in repeatable read isolation. So commit the transaction and change my isolation level to the highest one, which is serializable. Now in serializable isolation, I'll do the same again. Look at the BU books. There are 5 of them because I did have that 5th book inserted. Now another connection. We'll try to insert my SQL Server 2014 internals book. Well, here's the secret. I didn't write a SQL 2014 internals book. This one cannot be inserted because this guy is in serializable isolation. Phantoms are prevented. A new book that meets this criteria cannot be inserted. In serializable only do we prevent phantoms. Now, I don't want this book to be inserted at all, so I'm just going to cancel this and get rid of it. And then when this one commits, now an insert could take place, but I don't have any inserts to run at this point. So that is the 4 basic isolation levels in pessimistic concurrency. SQL Server 2005 introduced something they called optimistic concurrency. And here I say 2012, but it's actually 2005, 2008, 2008 R2, and 2012. Everything before 2014 had a behavior that was described as optimistic, but really wasn't optimistic. And I'm going to come back to this part of the demo after we talk a bit about optimistic concurrency. Kathy, if any other questions come up?
Not right now.
All right. Everyone's just so excited. They just want to see what comes next. I'm sure that's all it is. Optimistic concurrency still supports the isolation levels that we've talked about. However, it does it without locking. It does it by using something called version data. No locks are needed this is because the existing data is not changed, or we have a way to see the older versions of the row. We're going to see this with in-memory tables in just a minute. But I need to tell you that the optimistic concurrency that Microsoft introduced for snapshot isolation in 2005 is not true optimistic concurrency. The optimistic concurrency for the old snapshot isolation is optimistic for reads only. Now, this slide deals with true optimistic concurrency. No locks ever, no latches. I'm going to come back to this slide in a minute. But I do want to show you this last demo here. This is the older optimistic concurrency that we could use with snapshot isolation before we had in-memory tables. Whoops, what did it do there? Oh, that wasn't a whole command, was it? I need to get that out. I'm going to change my pubs database to read committed snapshots. I'm going to do my update. I'm going to change all the prices, but not that you guys would ever do anything like this, but sometimes people make a mistake when they do their updates. This is a big mistake. Instead of setting price to price times 1.1, I'm setting price to 1.1, which is not what I wanted. I do not want all my prices to be $1.10. But what's going to happen if another connection tries to look at those prices? Another connection will see the original prices. No locking, no blocking. This is optimistic concurrency. I will not see the uncommitted data, but I will not be blocked. This can happen starting in 2005, but only for selects. Inserts, updates, and deletes will take locks and will block each other. I don't want all those new prices. That's all I'm going to say about that for now. I want to talk about true optimistic concurrency in the time we have remaining. So, in-memory OLTP was introduced in SQL Server 2014 as a way to have truly optimistic concurrency, meaning absolutely no locks are taken ever. Updates do not change the existing rows. So here I have 3 rows in a table. I'm not going to dwell on how they're organized through this hash table, but I've got a row for Elizabeth in San Francisco, who makes 80,000. John in Charlotte makes 50,000. Jane in New York makes 75,000. If I want to do an update, hold on, I keep hitting the wrong button when I'm on the wrong screen. Okay, if I'm going to update Elizabeth, I'm going to update her salary. What SQL Server does is actually creates a whole new row for Elizabeth. So the old Elizabeth row points to the new Elizabeth row while the transaction is in progress. We've got 2 versions of the row. The first version was added at an old timestamp 20, and the new time, you know what? I'm getting ahead of myself here. Let's see. Let's go back here. You know, I think I'm missing a slide here. Just to give one more background piece of information about in-memory storage. In-memory storage has rows in memory, and each row has 2 timestamps. A timestamp for the time the row was added, and a timestamp for the time the row was removed. So it's like a birth date and a death date. That's the slide that somehow I'm missing here. All right, now we can see that here. In each row, there is a timestamp for when the row was added. Elizabeth was added at an old timestamp, and exactly what those timestamps mean, I'm not going to be able to tell you. At some old time 20, John was added at time 10, Jane was added at time 30. When was Elizabeth removed? This value infinity here means it's still there. It has not yet been deleted. John and Jane have also not been deleted. So if I want to do an update here, the row for Elizabeth is going to have its salary changed. A whole new row is created with the new salary of 90,000. What happens to the timestamps? While the transaction is in progress, the old row just has an internal indicator of a transaction in progress. The old row is about to end. The new row is about to come into existence and hasn't yet been deleted. And when the transaction commits, the end timestamp for the first row will change and the begin timestamp for the new row will change. And I thought, oops, and my animation is not working there. Darn, I thought this was going to update, so I apologize for that. In in-memory tables, there are only 3 isolation levels possible. Snapshot should be considered the basis. You should, in general, run in snapshot isolation. In that case, SQL Server doesn't have to do any additional validation. All it knows is just to show you the last committed value of any row. If there's a failure, a potential failure, you will error out. If a conflict occurs that could lead to a lost update, you will fail immediately. Repeatable read guarantees read stability. Serializable guarantees both read stability and phantom avoidance. So here we're back to the same terms that we started out with. Rather than go through a lot of words here that aren't going to mean a whole lot yet, I want to now go to the demo for in-memory. And I know we're just really hitting in-memory really fast. If you've never even looked at it before, I just want you to pay attention to the interactions between the sessions, just like we had for the pessimistic concurrency with our regular tables. So to create an in-memory table, I need a database capable of supporting in-memory tables. And that basically means any database. I'm going to create a new database called IMDb, which doesn't have anything to do with movies. It stands for In-Memory Database. And it needs a special file group. And I'm doing this in 2 steps. You could do it in 1 step. You could add the file group in the same command you created the database. But I'm doing this because I want to show you you can do this for any existing database. You can add a new file group with this property contains memory optimized data. I could take my pubs database and do this if I wanted. I could take my current sales database and add a memory optimized data file group. I need to have at least 1 file, which we call a container, because it's not a single file anymore. And I'm ready to create a memory optimized table. I'm going to allow snapshot isolation, and by default for memory optimized tables, you must specify an isolation level for every command unless you use this option and say, I always want to run in snapshot isolation. Actually, it doesn't say that exactly. It says elevate to snapshot, meaning if the base session is in the lower level of read committed, you will elevate to snapshot, which is a higher isolation level. But if I'm in a higher isolation level, it doesn't decrease to snapshot. I will show you that in the demo. So in my in-memory database, I'm going to create a couple of tables, one called sales orders in mem. And basically it looks like a regular table, except it has this option called memory optimized equals on. That's basically the only thing different here. There are different kinds of indexes. We have a hash index, which I don't have time to go into. The sys.tables catalog view tells me if a table is memory optimized. Durability, we're not going to talk about right now. I'm going to have a almost identical regular table, which we call a disk-based table, also with an index. I can delete all the rows if there were any, but I just created them, so of course there's none to start with. And I'm going to put 2 rows into each table. So these tables are even smaller than the ones in the pubs database, just to show you what happens in the different isolation levels. So right now, these are both tables I'm going to be working with. The data is almost identical. They both have order ID of 1, 2 and an order status of 1, 2. But I'm going to be changing the order status in my demos. So first I want to show you what happens with, well, just the fact that we are in snapshot isolation, which means we will not see any dirty data. So if we add 5 to the order status for the first row, not committing the transaction, I've added 5. This is the first row, order ID 1. I've added 5 with an order status of 6 now. That's the adding 5 I just did. But if another connection wants to look at that data, it will see the original value of 1. This is snapshot isolation. Snapshot shows you the way that the most recent committed values, the way it was before any current transactions started. Committing the transaction. Now this one can see the new data because it's now been committed. Well, I'm going to rewind that. Oh, and I forgot to take this with snapshot out. I don't need that when I have the altered database. I'm going to reset it back to the original values. So I want to show you a difference between memory optimized tables and disk-based tables as far as lost updates are concerned. SQL Server will detect a potential lost update, and it will give one of the processes an error. In disk-based tables, it's a little bit different. Let me show you what I mean. I'm going to go to snapshot isolation for my disk-based tables. That's your normal tables. I'm going to show you the current value. Oh, there's a keystroke that gets me out of grid mode. I keep accidentally hitting that. I'm going to do an update. I'm going to add 10 to order status in the first row and see the new value. It's now 11. Now another transaction is going to try to do the update, and it will block and wait to see what's going to happen over here. I've added 10 to the original value. This guy's trying to add 5 to the original value of the same row. This is a potential conflict. As soon as this guy commits, this one gets an error message and says, well, I can't add 5 because someone else has already added 10. And if I add 5 to the original value that was there when I started trying to do this update, I'll lose the 10 that the other one added. This is a potential problem. SQL Server detects it by making the second transaction wait, and then if the first one succeeds, the second one will fail. If the first one had rolled back, then this one could have succeeded. It waits to see if the first one's going to roll back or not. Since the first one committed, this one gets an error. Now, in memory optimized tables, it's a little different. In memory optimized tables, we want to reduce all of our weighting to the absolute minimum. So I have added 10, but I didn't add the 5. Only one of the updates happened. So in memory optimized tables, the exact same behavior, add 10, oops, yeah, that was the first value. I started with a 1 for order 1. I added 10, so now I have an 11. If the other transaction tries to add 5, change the data that's currently being changed by somebody else. Shoot. Oh. Watch this. It errors out immediately. The current transaction attempted to update a record that has been updated since this transaction started. The transaction was aborted. Well, since this transaction started is a little not true, but it's basically if this update succeeds, we'd have a lost update. So it is not able to succeed. It doesn't even wait to see if this guy is going to commit or roll back. Because there's a potential problem, it gives me the error immediately. So that's one difference between in-memory tables and disk-based tables. Disk-based tables will wait to see if the first transaction actually commits. Did those first users actually buy the tickets or not? Only if they actually buy them will my transaction be lost. If the first guys cancel or change their minds, then I can get them with disk-based tables. But with memory optimized tables, as soon as SQL Server sees there's even a potential of a conflict, it gives me the error immediately. So I want to look at a couple of the other isolation levels here because there are some other differences here. In pessimistic concurrency, it's really hard to see a difference between repeatable read and read stability. Repeatable read means you will continue to read the same values throughout your transaction. Read stability means the data you've read will not change. If the way that these are guaranteed is through locking, there is no difference between them. We guarantee repeatable read by locking the data, and once the data is locked, it can't change. But within memory tables, there is a difference between these. Within memory tables, I can look at the values and see, I'm just interested in these. I have a 2 and an 11. Well, actually, we should order by order ID. I have an 11 and a 2. If another transaction tries to change the value, we're still in the same situation. Sorry about that. I forgot to do something. I forgot. Oh no, that's what I wanted to show you here. That is repeatable read. The other guy was not able to do the change, so I will continue to see the same values. But what if I am in repeatable read isolation? I have to request it in the query. There's my data. The other transaction will try to make a change with repeatable read isolation. And something, all right, you know what, something, okay, that was it. I was still inside of a transaction I had not committed yet. I'm going to rewind. And I know we're over time a little bit. I think it was announced we might go a little bit past an hour. There's just a couple more things I want to show you here. So I'm going to start this again. I've got values of 11 and 2. I'm in repeatable read, which means I want to continue to read those same values. No matter what happens, I want to keep reading 11 and 2. So even if this other transaction is able to go over here and make this change, it thinks it changed it to a 16. I will continue to read the same values. This is repeatable read. I am reading the same values over and over, but the data actually changed. The data is not stable. And here's the catch. I asked for repeatable read, which means I not only want repeatable read, I want read stability. So when I come back here and try to commit this transaction, I get an error. This takes a lot of people by surprise, myself included. I'm still not, I'm going to come back to a couple of these slides in a minute. I want to just revisit this chart. And here I can explain the no and the yes down here under snapshot isolation. In snapshot isolation, you will not have non-repeatable reads, meaning your reads will be repeatable, but they may change out from under you. In repeatable read isolation, let me get my pen. In repeatable read isolation, not only can we not see changing data, but it will not change out from under us. These are two different things. Phantoms. In snapshot isolation, somebody can insert data that meets our filter condition, but we just won't see it. In serializable, nobody can even insert those values, and we will get an error if someone even tries to. The difference here is, do you see the value or do you get an error if somebody tries to change it? In repeatable read, as we saw in the demo here, we got an error just because somebody tried to change the data even though we don't see it. So how does SQL Server make sure that we get the behaviors we want? I jumped over a couple of slides here. In repeatable read, we have to verify that the data does not change. In serializable, we not only have to verify the data doesn't change, but that there are no phantoms. And this, when I say we, I actually mean SQL Server has to verify that. Behind the scenes, if there is not read stability, we get an error. How does it do that? SQL Server keeps track of all the data that's been read, all the rows that have been written, and the range of data that have been scanned. It also knows the end timestamp before it starts its validation process. To validate read stability after the transaction is over, SQL Server goes back and makes sure that at the end of the transaction, nothing is different than it was during the transaction. So we start this transaction at time 35. We read Elizabeth's salary, which is 80, and the transaction commits at 50. The post-commit validation looks at all the rows that we've read. Here it's only Elizabeth's, and if the end salary is the same as the value we read, everything's okay. If the end salary is different, it's not okay, and we get an error. Now, this may seem like it's an expensive thing to do, but in general, it's not. This only happens with in-memory OLTP. And do you know what OLTP means? OLTP is online transaction processing, and in general, we should only be using OLTP when we're changing just a few rows. In-memory OLTP is not designed to work with changing hundreds or thousands of rows. It basically works with just a very small set of rows at a time, or it works best. So it's not that much work. Phantom avoidance. That's confirmed by rescanning the data, which of course sounds like it's expensive, but it's really not. After the transaction is over, we have to go back and make sure that there are no additional rows of data in the scan set. All the rows are in memory all the time. There are simplified ways of rescanning the same data. This is only necessary if we're in serializable isolation, which should be your rarest option. And it's actually less expensive than what SQL Server does if you're using a disk-based table in serializable isolation, which is something called range locking. Range locking is actually much more expensive than this revalidation that we have to do. So I actually showed you most of this demo already. I know it was a really, really quick and dirty introduction to in-memory tables, but what I wanted to show you was there are some slight differences in the way that the isolation levels are handled in optimistic concurrency. The good thing about optimistic concurrency is that there are absolutely no locks and no waiting for your data manipulation. No waiting on locks ever. This only happens in snapshot isolation. What behaviors are allowed in what isolation levels is the main purpose of this chart, but in snapshot isolation for memory optimized tables, there are some unexpected behaviors that you need to test for thoroughly. So hopefully that gives you a more solid understanding of what the isolation levels are about. I don't expect you're going away from this completely understanding in-memory OLTP, but isolation levels are a concept that is important to have a good handle on if you're doing any multi-user application development. Concurrency models basically just tell SQL Server how to enforce the isolation level. Pessimistic concurrency says enforce it with locking and blocking. Optimistic concurrency says don't use locking, enforce your isolation levels by having older versions of the data available to us.
Kalen, that was so much information and wonderful information, and now we need to go download those books so we can learn more.
Right.
But I do have a couple of questions if you have some time. Two of them are related. One of them more for your older versions of quote unquote optimistic. What's the cost of performance? And then a related question for in-memory OLTP, what performance things you need to think about? For example, do you need more memory? Do you need to be concerned about TempDB?
Very, very good questions, Kathy. It almost sounds like I had a plant in the audience there because those are great questions. For the old semi-optimistic concurrency, your biggest performance impact is in TempDB. The versions are stored in TempDB. And remember, you only have one TempDB for the entire SQL Server instance, and all databases share the same one. So a large table that's being updated in snapshot isolation can make a major impact on your TempDB resources. You need to do thorough testing to make sure that you've got enough TempDB space for all of the tables, all of the rows that are going to be updated under snapshot isolation. So that is the biggest thing that people don't plan well for in the the disk-based snapshot isolation, the cost is possibly lots more TempDB. For the in-memory OLTP, TempDB is not used because everything is in memory all the time. You do need to make sure you have sufficient memory for all of the versions of all of the rows that anybody may ever need to access concurrently. So it's a memory versus a TempDB trade-off here. The good thing about the in-memory OLTP is you don't have to have memory for your entire database. You can actually just take one or two critical tables and make those in-memory tables. In-memory tables can interact with your disk-based table. So I can have my sales table in memory because that's the one that I'm hitting the hardest, and my customer table can still be a disk-based table, and those can be joined together with no problem. So you need to make sure you have enough memory for all the in-memory rows you're going to be affecting, but not necessarily for all your other data in the database.
Cool. I have one more question. You can decide if you can answer it or not. How does NoSQL database technology maintain data consistency?
You know, that I cannot address. I have barely touched anything involving NoSQL.
Okay. Fair enough. So that's all the
No,
questions.
there's plenty to keep me busy using just SQL Server. Keeps me more than busy.
I can imagine. Yeah. So but anyway, thank you so much, Kalen. And there's just so much to learn. But it's really great to learn about all these different options. It's just, take some research to figure out what's
Oh,
best
and
for the
sometimes
particular
it just
workload.
takes going over it multiple times. If this is the first you've been exposed to any of these concepts, then yes, it's going to be pretty overwhelming. But the more you see it, the more you think about it, the more you just try out some simple demos and just make it part of your basic understanding, it can become real powerful and a real good addition to your SQL Server knowledge.
Absolutely. Okay, well, thank you so much, and we'll have the video posted on the WIT website, and Kalen will have the slides and code on her website. So thank you so much.
SQLServerInternals.com, hopefully by the end of the week. Thank you so much, Kathy.
All right, thanks. Bye.
Okay, bye-bye.